Welcome to part 2. We're going to continue our discussion with the unit tangent vector, and we're going to start off by looking at a vector v, which in this case right here is a path in space, and it's going to be a linear path. You're looking at the variables there, and they just want us to find the value of the vector when t is 2. So I just plug in 2 into my vector right there. Let me go and zoom in here a little bit. Maybe that'll take. If we plug in 2, that's going to give us 4 plus 1, which is 5, 1 minus 2, which is negative 1, and the 2 is a constant, so it stays there. For question B, it says find the unit vector. Remember, when a unit vector, they're saying they want the length to be 1. So to get our unit vector, first we're going to have to find the value of the vector at negative 3. And be careful, this is negative 6 plus 1, so we're going to get negative 5. 1 minus a negative 3, which is 4, and the 2 stays a constant. Because I do want the unit vector, I'm going to have to divide by the magnitude. So we might as well go and find that. So magnitude, remember, is just the square root of 25, x squared plus y squared plus z squared plus 16 plus 4. And we get the square root of 45. So our unit vector for this would be negative 5, 4, 2 over root 45. That would be our length. Remember, these are in the same direction. The only different direction, can't spell direction. They're in the same direction, but this one only has a unit length of 1. And the reason we like that is because if something length 1, it's easier to scale it for other values later on. Find the next question, part C, says find the tangent vector. Not the unit tangent, not the unit, just the tangent vector. So that's pretty easy. So that's just our v prime, right? That's just v prime of t. And we can get that pretty easily. That's just going to be, let's see here, v. That's just going to be the derivatives, 2, negative 1. 2 is a constant, so it just becomes 0. So there's our tangent vector. Our unit tangent vector, again, I want this to be length 1. So now I have to find the magnitude of our tangent vector. And that's just the square root of, that becomes 4 plus 1, or root 5. So our tangent vector, use the correct notation, t of t, is going to become 2, negative 1, 0, over the square root of 5. And there's our answer. I know what y'all thinking. This stuff is pretty cool. I really like it. But how's it going to help me with my tangent line? I'm glad you asked. We want to find the line tangent to this curve here, this trace. Okay? This trace. And we want to find the line tangent to it. Well, first of all, remember, what shape is this? Hopefully you recognize this, because this would be something like saying x squared over 4 plus y squared over 4 equals 1. So yeah, this is going to be a circle again on the xy plane right here. And because of the t right here in the z value, t is increasing. So again, this is going to be our spiral. So we want to find the line tangent to a spiral at this point. So of course, the first thing we need to write any tangent line is a point. And they gave us that. Root 2, pi over 4. Well, we also need the slope of the graph. Well, how do we get the slope of the graph? Well, we have to look at the derivative. So I'm going to take r prime of t, and that's going to become negative 2 sine t to cosine t 1. So there's my derivative. But if you notice, the derivative is in terms of t. So therefore, we need to find t. So we need to find the t-value there. So to get the t-value, we're going to go back and look at our original function. Remember, this is the path that we are on. We also have to intersect this point. This path has to intersect this point. So we can use corresponding values. For example, if I look at the x's, I know that 2 cosine t has to equal root 2. If I look at the y's, I know that 2 sine t has to equal root 2. If I look at the z's, I know that t has to equal pi over 4. Which is the easiest one to solve? This one. And the reason why that works is because these intersect each other, my trace has to be on this point, because that's the whole idea. I'm trying to find the line tangent at this point, so it only makes sense that this will be on that point. I can use the corresponding values in order to solve for t. And if I were to solve this one, I would get the same answer. I would get pi over 4 here, but be careful. I also get 7 pi over 4. Over here, we would get pi over 4, but we would also get 3 pi over 4. So you just look where those overlap. But again, that's the easiest one to use. So to get the slope, or the direction vector, we want r prime of pi over 4. And this is not too bad to do. We get negative 2 sine of pi over 4, root 2 over 2. 2 cosine of pi over 4, root 2 over 2, 1. And that becomes negative root 2, positive root 2, 1. And then to write our new tangent line, just like in calculus last year, and then earlier this year, we will go r of t equals, start with your point, root 2, pi over 4, add to that your change, t, and you're going to put this, negative root 2, 1. We talked earlier about how we write the vector equation of the line, and there we have our vector equation of our line. It's more like, remember, it's like that b plus mx plus b form is really what we're using here. If I want to write this as a unit tangent line, it would be the same. It would be root 2, pi over 4, plus t over, and I find the magnitude of my vector here. That's going to be 2 plus 1, which is root 5 times negative root 2, 1. This is the case. In the next video, we are going to be talking about the relationship again about the tangent and the unit tangent and the unit normal. If you have a plane, if you have a graph tangent to a curve and normal to it, that forms two vectors, and those vectors are a plane. We call that plane the oscillating plane. That is the plane derived from taking the unit tangent and the unit normal. Think of it like if you have your hand. If you do your hand like this, right here. If you just have your hand. Right now, I'll show you. Right here. Hold on. So, very simple. If you have your hand, this is the oscillating plane, you have your tangent to the shape of it, like if you look at my lifeline, which is very long and happy. Wrong way. Long and happy. I have my tangent curve to it, and I have my normal curve to it. That plane will go around, no matter where my surface goes. That plane will always contain, that oscillating plane will always contain the tangent and the normal curve vectors there. So we'll talk more about those in another video. Anyways, I hope you guys enjoyed it. I'll see you all later. Bye-bye.